Hello again. We are continuing our discussion on derivatives and how they apply to real-world situations. Today we're going to talk about how the derivatives can affect the inflection and the shape of a curve as it's graphed on the xy plane. So let's get started. We need to talk about the second derivative again, and remember that is the derivative of the first derivative. So you take the derivative, that gives you the first derivative. You take the derivative again, that gives you the second derivative. So that's how you figure that out. And here's what it tells us. If you remember, the first derivative will tell you the slope of the tangent line. Well, the second derivative will tell you how those slopes are changing. So if the second derivative is greater than 0, what that means is that the slopes of the tangent lines, as I move from left to right, are increasing. So if I measure them, the slopes of those tangent lines are going up. So what that means is one of two things. Either the slopes are negative and they're getting less negative. That's one way that slopes can increase, or they're already positive and they're getting more positive. That's the other way that slopes can increase. Well, if you look at both halves of that, that looks like a smiley face. And so the way I remember that a function is concave up is to remember that smiley face and how that means that the second derivative is greater than 0. Okay. On the other side of things, if the second derivative is less than 0, that means that the slopes of the tangent lines are decreasing as I go from left to right, which means one of two things. Either the slopes are already positive and they're getting less positive, or they're already negative and they're getting more negative, and that looks like a frowny face. So the frowny face helps me remember that if the second derivative is less than 0 or negative, that means that the function is concave down over that period of time. All right, points of inflection. Well, before I talk about points of inflection, let's review what we know about the first derivative. The first derivative, when it changes from positive to negative, what that means is that the function is changing from increasing to decreasing, and there's a maximum on the graph of f of x itself. When the first derivative changes from negative to positive, that means that the function is changing from decreasing to increasing, and there's a minimum on the graph where that change happens. So now let's talk about what happens when the second derivative changes from positive to negative. When the second derivative changes from positive to negative, then the curve changes from being concave up, or a smiley face, to concave down, or a frowny face, and we say that there is a point of inflection where that change happens. Okay, and there's two examples for you right there. And then if the second derivative changes from negative to positive, what that means is that the function itself will go from being concave down to concave up, or from a frowny face looking graph to a smiley face looking graph, and there's two examples there. All right, we need to talk about stationary versus non-stationary points of inflection. All right, if a point of inflection has a slope of 0, then we call that a stationary point of inflection. Whereas if it doesn't, then that's called a non-stationary point of inflection. Okay, just some terminology because we will be talking about examples of those. Okay, so let's look at an example. I've got f of x equals 3x to the fourth minus 16x to the third plus 24x squared minus 9. Okay, I need to find and classify all the critical points. That's where the first derivative is equal to 0. I need to find the intervals where the function is increasing or decreasing. I need to find and classify all of the points of inflection. And I need to find intervals where the function is concave up or concave down. Okay, so dealing with the first and the second derivative here. All right, well, the first derivative is 12x to the third minus 48x squared plus 48x. So I need to be able to factor that to figure out when that's equal to 0. So that factors to be 12x times x minus 2 squared. All right, that means that that is going to equal 0 when x is equal to 0 and when x is equal to 2. All right, then I look at the second derivative. That means I take the derivative of the first derivative. That will give me 36x squared minus 96x. I can factor that as well to be 12 times x minus 2 times 3x minus 2. And that is going to equal 0 when x is 2/3 and when x is equal to 2. So notice that x equals 2 shows up twice. It's a critical point and it's a point of inflection. That's going to be important when we draw the graph of the function. So for the first derivative, there it is again, 12x times x minus 2 squared. The critical points, as we said, are at x equals 0 and x equals 2. So I'm going to set up a sign diagram to see where the function is increasing and where the function is decreasing. So looking at some point that's less than 0, if I plug that in, 12x is going to be negative, And x minus 2 squared, because it's squared, it will always be positive. So for every x that's less than 0, the first derivative is negative, meaning that the function is decreasing. Now if I pick a number between 0 and 2, the 12x now becomes positive, the x minus 2 squared stays positive, so the entire first derivative is positive, meaning that the function is increasing everywhere from 0 to 2. Then, because there's no change when I pick an x that is larger than 2, the function is increasing still for all x's that are greater than 2. All right. Since it switches from decreasing to increasing at x equals 0, there's a minimum at x equals 0. And since it doesn't change from increasing to decreasing or vice versa, it goes from increasing and then it levels off, and then it increases again, we're going to call that a point of inflection. Okay, so f is increasing from 0 to 2 and from 2 to infinity, and it's decreasing from negative infinity to 0. All right, now we look at the second derivative. There it is. Remember, we have points of inflection at x equals 2/3 and x equals 2. Now, I want to point out that these are possible points of inflection. They're not going to be points of inflection unless the second derivative actually changes sign from one side of each number to the other side. Okay? So here is my sign diagram again. This time it's for the second derivative. Picking some x that is less than 2/3, well, 12 will always be positive. But that number minus 2 will be negative, and 3 times that number minus 2 will also be negative. So the entire second derivative is positive, meaning that the function is concave up everywhere where x is less than 2/3. Then if I pick a number between 2/3 and 2, do the same thing again. The only thing that changes is that the last factor becomes positive, so now the entire second derivative is negative, meaning that the function is concave down everywhere from 2/3 to 2. And then finally, if I pick an x that is larger than 2 and plug that into the second derivative, the only thing that changes is that middle factor now becomes positive, so the entire second derivative is positive, so the function is concave up everywhere where x is greater than 2. All right. Now, since the function did change sign from less than 2/3 to greater than 2/3, there's a point of inflection, but because the first derivative wasn't also equal to 0, that is a non-stationary point of inflection. But remember, the first derivative was equal to 0 at x equals 2, and now the second derivative was equal to 0 at x equals 2. So what I have at x equals 2 is a stationary point of inflection. All right, so the graph is concave up from negative infinity to 2/3 and from 2 to infinity, and it's concave down from 2/3 to 2. All right, so here's a summary of everything that we've talked about. There's the function. We have a minimum at x equals 0. We have a point of inflection at x equals 2. It is increasing from 0 to 2 and from 2 to infinity. It is decreasing from negative infinity to 0. Okay, and now let's look at what the second derivative told us. There is a non-stationary point of inflection at 2/3, and there is a stationary point of inflection at x equals 2. So now let's look at where it's concave up and concave down. The function is concave up from negative infinity to 2/3 and from 2 to infinity, and it is concave down from 2/3 to 2. So that's how the first and second derivative can really help you sketch a graph for a function that you don't know what the graph looks like. So that's kind of a summary of all of that information. If you have any questions, please let me know, and I will see you tomorrow.